Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 5 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be tackling today. We say a function f from the natural numbers to the natural numbers, so a function from the positive integers to the positive integers. We call that function interesting if it satisfies this weird looking property here. That is that f to the f of k equals k for all natural numbers k. So what do we mean here by this kind of weird looking pyramid notation? Well, what we mean is, so suppose we have fn of d. This doesn't mean like the nth derivative of f or f of d raised to the power of n. This just means applying f n times. So something like this at d. Like so, there are n f's there. So that's kind of what we mean by this notation here. So what we're doing is we're firstly evaluating f of k. That would be some positive integer, say t. Then we're doing f t times on this k here, and that will give us some new positive integer, say s. Then we're applying f s times on k, and what we should end up with is k, and that's for all positive integers k. Our problem is we want to find all natural numbers L such that for any interesting function f evaluate, or f to the 21 of L, so f applied 21 times to L, spits out L again. Okay, so this is kind of a big problem and a lot to digest, so if you want to pause the video and just have another reread of this, but if you want to pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to solve this is we're going to start by taking an arbitrary positive integer a and an arbitrary interesting function f, and then considering this sequence of numbers here. So an, the nth term in our sequence, is defined to be equal to f applied to a, at n times, like so. And an alternate way of defining the sequence is an equivalent definition, is you start by saying a1 equals f of a, and then an plus 1 equals f of an, like so. Okay, so these are both definitions of the same sequence. The first thing I'm going to do is claim that our sequence of ANs is a periodic sequence. So it will do something for a bit, but then that chunk will kind of repeat itself and repeat itself and repeat itself and so on. And the way we're going to see that is because f is an interesting function, we know that this guy here, f of a, this thing here is just going to be equal to a. But then look at this thing here in the exponent. This guy here is f to the f of a. We don't know what that is, but it's going to be some positive integer, which I'm going to call b. So we have f to the b of a equals a. So let's just clean that up. F to the b of a equals a, and this is just for some positive integer b. But then notice that this thing here, from this definition here, is just a b plus 1. Oh, sorry, a b, sorry. So just plugging in n equals b. But then a b plus 1 is just equal to, from definition, f to the b plus 1 of a. But this thing here is just f of f to the b of a, like so. But we know f to the b of a is just a from the line above. So this is just f of a, and of course that's just equal to a1. So we get ab plus 1 is a1. So this b plus 1th term kind of tracks back to our first term. But then hopefully it's quite clear to see that then ab plus 2, using a pretty similar argument, will just be a2. ab plus 3 will be a3, and so on. So you're going to kind of repeat this sequence again. So once you get to b, you know you're going to start back at the start again at b plus 1. So that shows that our sequence of ANs is periodic. The next thing we want to do is actually consider the minimum period, because of course the b I just gave is a period of our sequence of numbers an, but it may not be the smallest period. But we know that a smallest period must exist. So we have m, we'll call it m. So m is our minimal period of an, like so. And one kind of very standard property of m, or the minimal period, is the fact that if we have some other period of our an, so let's t, so we know our sequence repeats every t, then we know that little m must divide t. So this is a pretty standard property of periodic sequences. Anyway, we have this guy here. The next thing we're going to notice is that m, or I guess for all I, we have the f to the f to the f of ai, of ai, of ai, like so. This guy here equals ai. So this just comes from the fact that f is an interesting function. But remember what I just said before, that if t is some period, then m must divide our little t. So if we just look at this guy here, we can clearly see that number there, let's call it bi, we see that after we apply f bi times to itself, it's going to repeat. So that must mean that for every I, we have the m divides f to the f of ai like so. So this thing holds true for every single ai. But notice if we just look at our definition up here, this fai in our exponent, if we just replace n with I, this thing here is just the same as f to the ai plus 1 of ai, just by looking at this thing here. So we have that m divides f to the ai plus 1 of ai. The next thing we're going to do is notice that if m divides ai plus 1, then just by looking at this line here, if we look at the ai plus 1 in our exponent, well, if m divides ai plus 1, then that means ai plus 1 equals, say, lambda times m for some lambda, positive integer lambda. So we can write this thing here, say, as lambda times m. Or actually, I'll leave it like here. But if m divides ai plus 1, then this thing here just equals f to the lambda m of ai. But remember, because m is a period of these an's, that means if you apply f m times to ai, then you're just going to get ai back. And that holds true for any I. And then, of course, just doing that process lambda times will just mean you're going to get ai, 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 ai. So when you finish your process, you're always going to be left off with ai, like so. So we have that if m divides ai plus 1, then this guy here just collapses down to ai. But if we just look at what that means m divides ai. So if m divides ai plus 1, then m must divide ai. Okay, so that's kind of what we've proved here. But then we can kind of continue this by induction. So if m divides ai plus 1, then it divides ai, then it divides ai minus 1, then it divides ai minus 2, and so on down to a1. So essentially what we've proven is that if m is a factor of any of the terms in our sequence, then it must be a factor of our first term in our sequence. And in fact, we can, I guess one thing I should have stated is we can define this function here from n equals 0. So if I go back and just say a0 equals just a, whoopsie daisy, a0 equals a like so, and then, or this equivalent definition, say from n being bigger than or equal to 0, we can start our sequence off from 0 and this all holds. So if m divides some term in our sequence, then it must divide our first term in our sequence, so namely a. But we need to show that m divides some term in our sequence, but that's already kind of done for us here, because we know that m divides this guy here. So we can look at the case, particular case where I equals 0. So we're looking at f a0, a0, and we know that a0 is just a. So we know that m divides this guy here, but f of a is going to be some number, and so we're doing f to that number, f applied to a that number of times. That's just going to be some term in our sequence. In fact, it's going to be that term of our sequence. So what we have is that m will divide some term in our sequence, namely this term here. And so by this inductive argument, m must divide our first term. So all in all, what we've proved is that our minimum period m must divide a. Let me clean up the whiteboard and we'll continue. Okay, so now what we're going to do is take a factor of 2021 and call it d. So d is some positive integer that divides 2021. And if you just look at the prime factorization of d, of 2021, you can work out that d must be one of these numbers here. So d must be either 1, 43, 47, or 2021. Now my claim is that f to the 2021 of d equals d, and this holds true for any interesting function f. Now let's prove this claim. But what we're going to do is kind of use the argument we just had before. So we're going to let a equal d, and then we're going to consider our an's. So an, remember, is just our f of f of f of so on of f of an. So they're of a, n times, like so. So this is what we had from before. Remember what we just showed was that our minimum period m must divide a. So we had that our period, or our minimum period, I should say, min period, which we called m, we know that that divides our start term a, which in this case is just d. But we know d is a factor of 2021, so if m divides d, then certainly m must divide 2021. But then if m divides 2021, then f to the 2021 of d, this thing here, well, because m divides 2021 is some multiple of our period, so that means this thing here is just going to collapse down to our identity function, and this is just going to be d. Because remember, 2021 is just some multiple of m, so we can write it as lambda m. So we're doing fm of d, fm, I guess one way of thinking about it is this side here is just fm composed with fm composed with, and so on a bunch of times, fm of d, and the number of fm's we have is lambda, and fm composed with fm of d. Well, notice that each of these fm's is just the same as the identity function, so we're just doing the identity function of on d a bunch of times, and of course that will equal d. So this proves our claim, f to the 2021 of d equals d, and this holds true for any interesting function f. The next thing I'm going to do is I'm going to claim that these are the only kind of d's that work. So for any d that isn't a factor of 2021, then we have that f to the 2021 of d is not equal to d for every single interesting function. Let me clean up the whiteboard and we'll continue. Okay, so to finish off this problem, I claim that if d is not a factor of 2021, so if it's not 1, 43, 47 or 2021, then there exists some interesting function f such that f to the 2021 of d does not equal d, so d cannot be like one of the solutions to our problem. So once we've proved this, that will solve our problem, and the solution to our problem will simply be the numbers 1, 43, 47 and 2021. But of course we've got to prove this claim. So this claim is that if d is not a factor of 2021, then there exists an interesting function f such that f to the 2021 of d does not equal d. And this is actually not too difficult to prove. We're just going to prove it by giving an explicit interesting function f. So what is this function? Well, we're going to say that for f of d is going to be equal to it's going to be equal to 2d. F of 2d is going to be equal to 3d, and so on. So f then all the way up to d minus 1, oopsie daisy, of d times d. This thing here is going to be d squared. But then f of d squared, we're going to loop back around to d. So basically for a multiple of d which is less than d squared, we're just going to kind of, when we plug it into f, we're going to give us the next multiple of d. But then when we go to d squared, we're going to loop back around to the start and give us the first multiple of d, so namely d. And then, so this is what holds true for all of these, and then just for every other integer n, is just going to be the identity function. So fn of n equals n, and that's for every other number. So every multiple of d bigger than d squared, and every non-multiple of d. And now you can check that this function here, in fact, is an interesting function, because essentially it's got, well, you can just kind of check from the definitions of an interesting function. It's a little bit laborious and a bit boring, but notice that this function here has period d, and because d does not divide 2021, then we cannot have f of 2021 of d being equal to d, and that kind of proves our claim. Now, I've kind of just speed run through that, so if you want to go through the details yourself, please do so, but essentially this is the key thing, to write down this function here, check that it's an interesting function, and check because d is not a factor of 2021, f to the 2021 of d cannot be equal to d. Anyway, thank you for watching. This has solved our problem. We have shown that the solutions to our problem is just 1, 43, 47 and 2021. Thanks for watching. I'll catch you in the next one. Have a great day.